Hey, so in this unit we've been toying around with the idea, the question, what are the factors that affect how strongly objects interact with each other? Okay, so we have the first activity that we did was we watched this video, which I will show you real quick, about the conducting rod with the two balls going around the Van de Graaff. Here we go. And we could see that the two balls always stayed in the same place. They're lining themselves up with the electric fields around the Van de Graaff machine, is what's going on. We have this positive charge that's emanating outward from the Van de Graaff, and those balls are lining themselves up with it. Okay, so we come here, and when the conducting rod was brought close and around the Van de Graaff, it stayed in the same formation all the way around, so the lighter colored ball was closer and the darker colored ball was farther away. This happened because there is an omnidirectional force field around the Van de Graaff, and the conducting balls consistently line themselves up with it. Okay? And I'm going to even change this. I'm going to say an omnidirectional electrical field, because that's more precise there. Okay? So then we had the space around a charged object simulation. Let me get in there. Okay, so that one looked like this, and we could trace the force pointers. So we had all these lines that consistently line up pointing away from that central stationary point, okay? So when the positive charge was moved around a stationary positive charge, the green arrows always pointed outward from the stationary central positive charge. So that's showing that the electrical field lines, the electrical field is going outward from positive charges, okay? This happened because like particles repel, okay? And that's also just the way that electrical field lines are written. Positive charge has a stronger force, a stronger potential energy than negative than a negative charge does. So that's why that shows those forces going outwards. When the positive charge was moved around a stationary negative charge, let's look at that real quick. So now we're going to set it to negative, and we're seeing that those pointers always point inwards towards a negative stationary charge. Okay? So the green arrows always pointed inward towards the stationary central negative charge. This happened because oppositely charged particles attract, and also because the electrical field lines always go inwards towards a negative charge. So you've seen my metaphor for like the grandma always sending out cookies, she's the positive charge, and then the Cookie Monster is always taking in those cookies, he's the negative charge, okay? So how do factors like distance and amount of charge affect interactions between objects? So we had the Van de Graaff and the tape. So here's that demonstration. Okay, so that tape is definitely attracted. You can see it pointing up towards it even all the way down here. It's wanting to stick for sure. Okay, let's unzap it. Okay. Now I want to see, ooh, goodness. Okay, turning that off. Now I want to see what's happening with this balloon. So there is a charge here for sure. I mean, it's definitely attracted there. It's definitely sticking to it. I wonder, wow, do you see how far away I am from the Van de Graaff though? And the Van de Graaff is turned off and it's still attracted. So what we're seeing there is an electric field around the Van de Graaff machine. It is a positively charged electromagnetic field, and you can tell how far it goes out because when the ruler with the tape in it is way out here, that tape is still attracted. In contrast, that balloon has a much weaker field around it, so that only, an inch or two away from the balloon, that tape is kind of fading and not sticking up like it was. So let's come back here. Okay, so when the tape was brought close to the Van de Graaff generator, it attracted. This happened because the Van de Graaff generator had a strong charge, and when the tape was brought farther away from the Van de Graaff generator, it still attracted. So when the tape was brought near the balloon, the tape was not as attracted compared to when the tape was brought near the Van de Graaff. And this happened because the Van de Graaff generator had a stronger charge than the balloon. So we have this idea in activity 1, this idea of the electric field around the charged object. And then in activity 2, we have this idea that the charge is stronger the closer that you are to that charged object and weaker the farther away you are. Okay, so then we had a simulation called the strength of electric forces simulation. Let me get there. All right, so this one, okay, and what are our questions here? When the charges were brought close together, the yellow force arrows were very long, indicating a strong attractive or repulsive force. So yeah, when they're close, the arrows are super long. When they're far away, the arrows are shorter. So when the charges are pulled farther apart, the yellow force arrows are much shorter, indicating a weaker attractive or repulsive force. And this happened because the electrical fields, just in general, electric fields are strongest closest to their source. Okay, so when one of the charges increased in strength, both yellow force arrows increased in length and strength. When one of the charged particles, and let's just look at that real quick. Here we go. Okay, so we have one super strong particle and one like kind of weak particle, but you can tell, so they are not as attracted as they were when both of them were super strong, but still when they get close, there's still quite a lot of attraction. But if we have two weak particles, then it's really going to take a lot for them to get super attracted to each other. Oops, I tried to do that. Yeah, they have to get pretty close before there's a strong attraction. Okay. Let's see. So this happened because the electromagnetic field around a charged object is omnidirectional and is strongest closest to its source. When one of the charged particles was removed, the electromagnetic field around the remaining charged particle became even in all directions, and there were no forces acting on it. Okay, so let's look at that real quick. So if we say use just one particle, then there are no forces acting on this. So it just has this nice, like, spherical electromagnetic field around it. Same thing if it was positively or negatively charged, but then that field would be going inwards as opposed to outwards. Okay. All right, activity 3. How does our model of charge interactions connect with a variety of phenomena? So now we're talking about the Franklin's bells and we're talking about lightning. And so let's get to that one so we can look at that simulation. Ringing the bells. Let's see. Okay, so we have this situation, right? We have the Van de Graaff generator connected to a can by a wire. We have a ball hanging down between them and then a can that was not connected to the Van de Graaff over here. So before the Van de Graaff was turned on, the ball hung motionless between the two cans. This happened because the charges were neutral, so the forces were balanced. That ball does not have a charge. Nothing in there has a charge. All the positive and negative charges that are there, which everything has charges, right? But they're balanced, and that's what makes the difference there. So after the Van de Graaff had been running for a short time, the ball moved towards the can that was connected to the generator. And this happened because the neutral ball was attracted to the charged can, right? A charged object will attract a neutral object to try to balance its charges, right? After touching the can connected to the generator, the ball moves away and swings toward the can not connected to the generator. So this happened because can 2 is neutral, so the charged ball is attracted to it. The charged ball is also repelled by like-charged can 1, right? So what's happening is that you have this charge. Hold on, let me show. Okay, so why did that happen? Right, so we have this charge that's coming from the Van de Graaff machine. It's charging up this can with the same charge. That positive charge is spreading out here to the can, right? So charged object attracts a neutral object. It comes over here, gets the charge from the can, and then it's repelled, right? Because we have two like charges that are together. So that ball then wants to move away from it, and so it goes over and it bumps the other can, and that can was neutral, and now it has that charge too. So then it's repelled from that one, it goes back to the other one, and it's going back and forth, right? But as soon as the Van de Graaff is turned off, it kind of calms down and it stops, right? Because now that charge has hit this can, and it's just gone out into the system. It's not being produced anymore. So they're all, they've all regained that neutral charge. But, sorry, I said that wrong. They didn't regain the neutral charge. They all had the same charge there together. The system had balanced out with that positive force field around it, right? But then when the woman put her hand up to that pop can, then the pop can was like, oh, sweet, a neutral object. I can release that charge into the hand. And so it did. That started ringing again, because then all of a sudden, like, it wasn't all the same charge anymore. That can, the can number 2, had released its charge, so now it had a weaker charge. So now that ball was moving back and forth between them, because it is trying to avoid the stronger charge, right? When we have a strongly charged object and another charged object that's the same charge but not as strong, it's going to try to avoid the stronger object. Okay? All right, we're close to the end of the video here. All right, so that's that one. And that is the end. Okay, so if you are able to understand what's going on and like not just fill this in with just the words that I said, but like because you really understand what's going on, then you're going to do great on the test. It all follows this very closely and you're going to be fine. So good luck. We'll see you later.